So the major question for this unit is going to be, why exactly do molecules exist in the state that they do? So why is water a liquid, and why is carbon dioxide a gas? And in order to answer that question, we actually need to understand how those molecules exist in the real world. Specifically, what shape do they assume? And in order to answer that question, we are going to have to learn how to draw the Lewis dot structures for these molecules. In order to do that, we need to quickly review how to determine the number of valence electrons each element has. So just as a quick review, remember, to determine valence electrons, we can use the periodic table. And we know that group 1 right here has 1 valence electron. We know that group 2 has 2 valence electrons. Remember, from this group here, for the most part, it's 2 valence electrons, because remember, the d orbital is 1 energy level lower than the s orbital, but we don't tend to use these metals, and I'll explain why in a second. 3 valence electrons, 4 valence electrons, so it just increases as you go across. Now, I just said, as I'm writing this out, I just said we don't tend to use these elements because they're metals. And what I meant by that is that for the compounds we are going to be creating in a second using covalent bonding, right? Water, carbon dioxide have covalent bonding. You need 2 nonmetals. So we're specifically going to be looking at this region over here, right? To the right of your staircase, and then also hydrogen. Okay, so that's how you determine valence electrons. Now I'm going to show you how to draw the Lewis structure.
All right, so now that we've reviewed counting valence electrons, we're going to talk about how to actually draw the molecules that we've been studying so far. And so these diagrams that we're going to draw are called Lewis dot diagrams. And I use the following acronym to remember how to draw them. So the first thing we need to do is we need to count our valence electrons. Okay. The next thing we're going to do is we are going to share electrons. Next, you're going to add lone electrons to your outside atoms and then to your central atom. And then finally, you're going to count the valence electrons you used again. So instead of trying to explain each of these, what I'm going to do is I'm going to show you 3 different examples and go through these steps. All right, so for the first molecule we've got water. All right, so the first step I have is I need to count my total number of valence electrons. So if you look at your periodic table, hydrogen has 1 valence electron, but there are 2 hydrogens, so that's a total of 2, plus oxygen, which has 6 valence electrons, so there are a total of 8 valence electrons. All right, that's step 1. Next, I need to share electrons. So oxygen is going to be my central atom here, and I'm going to share electrons like this. All right. So this is a covalent bond. This bond right here represents 2 electrons that are being shared between oxygen and hydrogen, right? Because this is going to be a covalent molecule. They're sharing electrons between them. Then I need to add lone electron pairs to the outside atoms and then to the central atom. So keep in mind, every atom wants to have this perfect octet, 8 valence electrons. The only exception is hydrogen. Since the noble gas for hydrogen is helium, hydrogen is actually happy just having these 2 valence electrons. So normally I would add an additional 6 electrons around the atom in order to have it have a total of 8 valence electrons. But hydrogen here, both of these hydrogens are happy with just 2. Oxygen, however, wants to have a total of 8 valence electrons. So it already has 2 from this bond, 2 from this bond, so it's got a total of 4. So it needs an additional 4 electrons, and we represent that as pairs of electrons. So there are 2 different ways I can draw this. I can draw it with dots, so I can show 2 electrons here and 2 electrons here. Okay. The easier way, personally, I feel, to draw this is instead of showing dots, you can represent 1 pair of electrons with lines. So you can show it with 1 line on top and 1 line on bottom. All right. So notice oxygen now has 2, 4, 6, 8 valence electrons. It is content. So I've finished the third step. The last step says count the number of valence electrons used. So I need to make sure I'm only using 8 valence electrons. If I'm not, I'm in trouble. So I've got 2, 4, 6, 8 electrons I'm using. I'm good to go. Now, this is just a generic drawing of my Lewis structure. However, this is not how it exists. Atoms, because they've got electrons on them, they're going to try and avoid one another as much as possible. These lone pairs of electrons are also going to cause some repulsions because electrons are negatively charged. They will repel the electrons on the hydrogens. So what we have to draw is the proper diagram using what we call the VSEPR model. Okay, and what the VSEPR model basically tells us is exactly what I just said. The atoms are going to be as far apart from one another as possible to minimize their repulsions of one another. They're going to be as far apart as is physically possible based on the fact that you've got these lone pairs of electrons as well. And so the way that we determine what this will look like is we're going to be using a simulation. So let me show you what water would look like first.
So here's the website here. Okay, so this website was provided to you. If you go and click model, okay, I'm going to actually recreate the model that I have for water. So remember, water has 2 hydrogens. I've got 2 hydrogens right here. Okay, and then it also has 2 lone pairs of electrons. Let's quickly look at that. You see 2 lone pairs. And so when I create this, I'm going to add 2 lone pairs of electrons. Okay, so this is using the VSEPR model. Notice I've got 2 pairs of electrons on top, and then my 2 atoms are pushed downwards into this bent shape. Okay, so when you draw this, you can't draw it with looking linear like we did before. So how could I draw this? Well, this is how I would draw this molecule using the VSEPR model.
So as you noticed, you had oxygen, and then you had your 2 hydrogen atoms going this way, and then you had your lone pairs of electrons on top like this. So I'm going to represent it like this. All right, if you want to just do like 2 on the side, that's perfectly fine. But what you'll notice is there wasn't one on top and one on bottom, right? Because the electrons are going to be, those 2 pairs of unshared electrons are going to be as far apart from one another as possible. Okay, yes, I know you're not quite comfortable with this yet, so let's look at 2 more examples. I've got PBr3. So my first step is to determine my total number of valence electrons. Phosphorus has 5 valence electrons. Bromine has 7, but there are 3 bromines. So I've got a total of 26 valence electrons. All right, now I need to share. So I'm going to put phosphorus in the center, and I'm going to draw 3 bromines coming off of phosphorus. Okay. Then I need to add lone pairs. So keep in mind, every atom, except for hydrogen, wants 8 valence electrons. Okay, that is a stable octet. So bromine right here has 2 already. So I'm going to add 4, 6, 8. And notice I added the lone pairs not here because they're already bromine's already sharing 2 electrons right here. I'm sharing them on the opposite sides, right? 2 on the sides, 1 opposite of the bonds. Okay. For bromine down here, again, I need to add 6. So I have 2 already, 4, 6, 8. For bromine here, I've got 2, then 4, 6, 8. Now I look at my central atom. Phosphorus has 2, 4, 6. So I'm going to add 1 lone pair here. All right. Now I need to count again to make sure I'm using the correct number of valence electrons. 2, 4, 6, 8, 10, 12. 14, 16, 18, 20, 22, 24, 26. I'm using the correct number. Now let's quickly create this molecule in my simulation with 3 single bonds and 1 lone pair and see what that would look like.
All right, so for PBr3, I have 3 bromines on my central atom, so it looks like this, okay? But then I also have 1 lone pair of electrons. So here's the shape here, you can look at it. Notice the lone pair of electrons before, when I didn't have the lone pair, looked like this. They were all on the same plane, okay? But as soon as you add that lone pair of electrons, this is the shape that you have. So I'm going to show you right now how I would draw this, but notice you've got 1 lone pair of electrons on top and then 3 moving downwards.
All right, so what you should have seen is the following. Obviously, it's not the nice 3D image that the simulation created, but you've got your bromines and then a lone pair on top. Okay, obviously, I also could have flipped this so the bromines were on top. You can draw it whichever way you want, just making it clear that the bromines are going to be, or it could be off to the side or the other way if you want to. But as long as the lone pair is on top and the bromines are going on in the opposite direction. All right, let's look at one more example. Sulfur trioxide. So sulfur has 6 valence electrons. Oxygen has 6, but there are 3 of them. So that's a total of 24 valence electrons. Okay, I'm going to share first. So sulfur with an oxygen, and an oxygen, and an oxygen. All right. Now I need to make sure everyone's happy. So 8 valence electrons, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, and then 2, 4, 6. I need a lone pair on top for sulfur. Before I jump the gun and draw it using the simulation, let's count total number of valence electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Oh no, I'm using too many electrons. So in this case, when you're using too many electrons, I now, instead of using a single bond, I now know I need to use a double bond. All right, so all a double bond is 2 single bonds together. So instead of sharing 2 electrons, I'm now sharing 4. So if you keep that in mind, I now need to get rid of some electrons because right now oxygen has 2, 4, 6, 8, 10. So I'm going to get rid of, doesn't matter which 2, but I'm going to get rid of those 2. Sulfur then has 2, 4, 6, 8, 10. So I'm going to get rid of that lone pair there. Now I'm using 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, and I am good to go. Let's see what this looks like using the simulation. All right, so the correct model is actually exactly what we just drew. However, I've got one last thing that I need to add on, one last concept. All right. A question you might be asking is, how do I know where to put the double bond? How do I know it goes here versus up here or over here? Well, the answer is you don't. And in fact, I'm going to blow your minds. This double bond doesn't truly exist, and these single bonds don't exist. Instead, what exists for SO3 is an average of these 3 bonds. So it's an average of a double bond, a single, and a single together. That would be, if you think about it, I'm going to jump the gun in introducing something, but that would be if we called a double bond a bond order of 2. We said it was 2 because it's double, 2 is double. And a single bond is 1, and another single bond is 1, and we divided that by 3. The average, because I'm averaging these bonds, a double, a single, divided by the 3 spots, that would be a bond order. And don't freak out about the word bond order. It's just saying the strength of the bonds, right? Single is 1, double is 2, of 1.33. How the heck do I draw a 1.33 bond? That's a single, that's a double. What is a 1.33 bond? Well, the answer is we don't have a very good way of drawing it. Instead, we draw it like this. We show all of the 3 different positions where the double bond could be, but doesn't really exist, because what really exists is that average, and we call it a day. So I literally just draw the double bond in all 3 locations. I say we are averaging, and then I leave it at that. This, what I'm drawing right now, these 3 different versions, this is known as resonance. So when you don't have just a single bonds or just double bonds, when you have this situation where you've got double and single, and it's actually what exists is an average, we call that resonance. Okay, so we'll be looking at more examples of this, but just knowing that the key point here is that last step of counting the valence electrons used. If you're using too many, then the response is you need to create a double bond. And if a double bond isn't enough and you're still using too many valence electrons, maybe you might need to use a triple bond.